so this use case here is partly a set of mechanisms that have evolved over time to try to wean people off v4, or at least move v4 out of certain parts of the network. But looking at it with a more, dystopic view, then it's a way of, allowing people to run v4 forever. We'll see where this ends up. So MAP stands for Mapping of Address and Port. It's a technology that's come out of Paris, actually. There's a great guy. He's, what is he now, 72, Rémi Depré, who came up with this stateless address mapping, which is a way of statelessly looking at either v6 addresses, figuring out and calculating v4 tunnel endpoint addresses, or the other way around. So this mechanism is, this set of mechanisms are completely stateless. We'll just say, v6 is finally going up and to, up over time, and we're seeing, reasonable growth curves. What we are seeing, though, is that the original transition story we had, how do you want to go from v4 to v6? The original plan was, by the time we ran out of v4 addresses, everyone would have moved to v6, so we would never run out. We would never get to that point. And we were going through, these phases where, we started with v4 only. We went to dual stacks. So everyone had v4 and v6. Initially with building overlay networks, then moving to native dual stack, and then doing the reverse, which is build overlays for the v4, and then end up with essentially a v6 only network. That plan failed horribly, of course, as we know. We did not move to v6 before we ran out of v4. So what we're doing now is sharing v4 addresses among more and more people. The nice properties of that, from perspective of inventing new stuff, is that it forces tunneling in some sense, right? Because when I give the same IPv4 address of an ISP, and I give the same IPv4 address to 1,000 of my customers, I can't do IPv4 forwarding anymore, right? Because they all have the same address, and most forwarding hardware can't forward based on random other identifiers in the packet, right? They have to forward on the v4 address. So you have to encapsulate this and build overlays anyway. So this is the IETF clusterfuck. Is there a good French word for that? There must be. We argued and we argued and we argued, and we filled in every little cell of the solution matrix to come up with all these mechanisms, and all these cool names, and all the ones with RD in there. That's for Rémi Depré that he invented. So we have the German arm here. This is the Chinese guys, at least up until here. This is the French sort of satellite down here. This is also a French one. This is Microsoft doing this one. It's a guy from Boeing doing that one.
Where are the Americans?
Yeah, well, if at least representing an American company, we were kind of for once the diplomats trying to build consensus here, right? So in the end, they're all the same. The IETF has a funny restriction. Although RFCs are a product of the IETF and an IETF working group, there are individual authors on these RFCs. And the IETF, although they have lifted that rule for these document set, had a limit of 5 authors per document. There were lots of people who wanted names on documents. How do you solve that? Well, you create more documents. So to some extent, that's what has happened. But all the places here where you have FD.io logo, those are the mechanisms that we support in VPP. and they're essentially all the same. I mean, it's exactly the same graph nodes. There's might be an if statement or not, but they're essentially doing exactly the same thing. So yes, so many of these branches were like, oh, here's the unifying standard, and of course we had. I don't think we had. Oh yes, so 4RD-U, that was the unified that should cover all of them. But we'll see what the market figures out. They are essentially all the same anyway, so it doesn't much matter. So what some of these technologies or the initial deployments have been to do CGNs, carrier grade NATs. So you have a NAT running in your home. So this is for service providers typically, right? So you have a NAT running at your home and you have a NAT running at a service provider. They're both stateful, and you translate the packets twice. And that works perfectly fine. I mean, someone on YouTube have shown you can plug 30 NATs back to back and see the packet traffic flows perfectly nice. Of course, you can't run. You're dependent on the cloud, and you're dependent on some third party to act as a rendezvous point for for all your application traffic, because no one can reach you directly, right? But that is just an effect of the v4 internet today, right? You cannot have end-to-end communication directly with IPv4 anymore. So what we do is, let's see if we have some slides here. So that's one option. We run NAT here, we run NAT there, stateful. The next step, which was up in, it's about 20 minutes walk from here. The other mechanism was invented, or at least given its name, which is called DS Lite, or quite a few bottles of wine apparently, which is, let's take away the NAT here and just do the NAT centrally. So that's called DS Lite. And that tunnels private v4 addresses over a v6 tunnel into a stateful NAT device. Stateful NAT devices are kind of hard to build, right? You have to ensure that the traffic is symmetric. You have to maintain all these state entries. If you want some sort of high availability, you have to synchronize state across boxes. So it's expensive. Coming from Cisco, expensive is good, right? We can sell you bigger boxes and charge you more money. So as an alternative, we came up with MAP, which is keeping the state at the CP close to the end user as possible, and have this function here, stateless, which has some very interesting scaling properties, and makes, I think this use case, at least in my mind, is kind of the perfect VNF, the virtual network function. It's actually one I can understand, which doesn't apply to many of the other use cases. And it makes a lot of sense, right? I have a tunnel already. It's stateless, so I can just scale it out sideways. No dynamic state. Well, this is just a picture of how we picked between some of these different solutions. It was a coin toss. Didn't really matter, though, because we ended up standardizing both sides of the coin anyway. What we do with MAP is to say we forward on the ports. So A plus P, address plus port forwarding. So to some extent, we're saying that, well, now the network layer, we're extending the IP header into the transport space. So that those 8 bytes that the transport guys thinks are theirs, they're now ours. So we forward on the port space. And the way we do this in MAP is we just allocate fixed set of ports to each customer. So everyone gets the same v4 address, and we give ports 1,000 to 2,000 to you, and the ports 2,000 to 3,000 to you. We do it that way. So it's a static allocation. I think the smallest allocations I heard about is sort of in the range of 16 or 64 or something. 16, I think. I think some people are running operational networks with 16 ports. The consequence of that is it's not that you can only have 16 TCP sessions up at the same time, right? You can have With an address-dependent NAT, you can have millions of sessions with 16 ports, but you can only have 16 sessions to the same destination port, right? Destination address and destination port on the other side. And the way we do this is by specifying an algorithm or specifying a set of rules that of which bits in the v4 address and which bits in the 16-bit port range should be used to generate an IPv6 address. We have a tool that allows you to configure these, so you can drag these lines around in this tool. Here's the URL up here, because just getting the gist of this idea is kind of hard. So we do the v6 allocation just like we do normally. There's no thinking about v4 at that point, and then you just say a set of bits, embedded address bits in the v6 prefix you use to generate v4 addresses. So if you have your last /24 of v4 public v4 space, you then map 8 bits from the v6 prefix to generate the v4 suffix, and 8 bits in the v6 prefix to generate the port range. Don't ask me why these are in the middle. It's complicated. And this simple single rule allows, in this case, to have 64,000 users. Right, so this is 64,000 subscribers just with this simple rule in a /24 of v4 space. And you could, trivially have so the downside from a VPP perspective is that, well, that small a lookup table is not the challenge, right? Because everything just fits in the smallest cache you can imagine. But there is another option here, which is called lightweight 406. So again, all the same thing, just that instead of doing an algorithm to map these bits back and forth, it has a big lookup table. And that's nicer from a VPP perspective because, you can imagine having a few million entries there. So at least there's a little bit of, you can test what happens when you run out of L3 cache for your tables, for example. And in the case, you want to scale this out, you just replicate that table across multiple devices. And typically, you would scale this with ECMP such that the BRs, so the tunnel concentrators address, is a v6 anycast address. So the routing system in the network will just nicely load balance traffic across all your devices. And traffic doesn't have to be symmetric. Traffic coming from the v4 internet can hit a different BR than traffic coming from the customer. That doesn't really matter. Yeah. So here's all these numbers. What is 7598? I guess that's the DHCP option. Isn't 7599? Oh yeah, 7590. I thought there was a few more. But yes. So this is kind of the first project that Pierre and I did in VPP. It's in vnet/map if you want to look at it. We implemented all of these, including IP fragmentation support, which is probably the most complicated part of the code. Did I say yesterday that we shouldn't do fragmentation? Yeah, I think I did. So as I said, the mechanism in itself is based on building a tunnel, an overlay, and it's stateless, and it doesn't require anything else. I mean, it's a completely autonomous mechanism. You can plug it straight into your core router. You don't need anything else. Other support systems. And that's probably typically what you would do. I mean, you would take bare metal hardware, plug it straight into a big router, with 40 gig or 100 gig interfaces. We are also looking at, see how well we can make this perform in containers, which is another way of deploying this if you wanted to share that hardware with other functions. So figuring out, how to implement this, we could certainly. You could have imagined, if you just did this on DPDK, you could just have taken your Ethernet frames in as v4 packet and and did done v6 frames out directly as a DPDK application, you didn't have to do v4 or v6 forwarding here, or you don't have to do act as a router as such. Although these tunnel RFC says you should decrement TTL and so on. But what we did was doing it as a VPP node. We attach ourselves to the v4 lookup node by setting the adjacency lookup next index to point to v4 map. Encapsulate the packet in the v6 header, send it to the IPv6 lookup function, which goes to IPv6 rewrite and then interface output. And the reverse is the same. We get a v6 packet in, hits v6 lookup, does a lookup in the adjacency, gets to the v6 map node that decaps, goes to v4 lookup, and then v4 rewrite. And these other nodes are the exception paths. So these paths are dual looped. These ones, I think, are all single looped, right, Pierre? So the sort of challenges here are, what do you do when you get a fragment? So if you get the first fragment, we create the fragment cache entry, which is a 4-tuple entry, such that we can, when we get a second fragment, doesn't have the UDP or TCP information, which we use to determine to do forwarding, right? So we require TCP or UDP ports. We do a lookup in the fragment cache and forward based on that. If you get fragments out of order, well, then what do you do? And I don't know if you guys know, but I tried to figure out how does actually fragmentation look like in the v4 internet, and it's pretty hard to figure out. I mean, there's few research papers back, decade or more ago that where people were looking at fragment behavior, but it was very hard to figure out, even from relatively recent packet traces. What's the length of the fragment chain? How many of them are in order, out of order? I mean, imagine you have a router somewhere in the internet that doesn't do flow classification properly. So it does ECMP, it would find a 5-tuple on the first fragment and do ECMP-based hash on that. Then the second fragment, it would either try to do a 5-tuple on the same offsets and certainly get it on a different path, or it would do a 3-tuple and do a different path. I think most routers do this correctly by doing a 3-tuple if you see a fragment. No idea what DPDK does. I'm sure it's different depending on Nick, but that's how you should do it. But you could end up with out of order fragments, and what you have to do then is to buffer the packet. So what we tested this with and developed it for is doing 100 million packets per second. How many seconds do you want me to buffer this packet? Not the RFC says for v4 it says 15 seconds, for v6 it says 60 seconds. So I'll buffer 100 million packets a second for 60 seconds. Yeah, right. But yeah, so what we do is, I think we have a maximum 100 millisecond. We maximum buffer for 100 millisecond. I think we by default only buffer 1,000 packets, and we limit the fragmentation chain to, is it 3 or 5 or 2?
I think by default we don't buffer.
Oh, and by default we don't buffer at all, right? Yeah. But that's configurable. But it's a circle buffer with very limited size. So if someone tried to attack, VPP would fare well, but it would be a consequence for legitimate fragment traffic. Last I looked at, I tried to get some packet traces. I've been working with some providers to figure out how fragments work, and pretty much all of it is just DOS attacks anyway. Either it's it's extremely big packets, like 64K packets, fragmented in so many parts that the chance of them all making it across the network is very little. At least the ones I saw didn't reassemble, or it's people doing queries on. There's a few queries you can do. There's a certain domain name which you can do lookup. I think it's set up to prove that you get a really large replies in DNS, and people use these for DOS amplification. or you can do. Not quite sure why anyone would provide that service to people, but it's there. So you know, if you just drop fragments, it wouldn't be a problem. We did, you know, partly for an exercise, implement it as well as we thought it could be implemented in VPP. You know, so essentially we do virtual reassembly, right? If we get the fragments in order, we'll just put an entry in the fragment cache, forward the packet, and forward the next one with you know, only that amount of state. Of course, then if you know fragments hit two different, you know, in different instances of VPP, the second fragment will not make it through, right? And with all these tunnel mechanisms, you have inner and outer, the possibility of inner or outer fragmentation. So in V4, we can do inner fragmentation, right? Because the endpoint will reassemble. In V6, we can't. So if you carry, you know, you build a tunnel which carries V6, you have to reassemble on the end of the tunnel. But you know, luckily in this case, which always carries V4, we can either do fragmentation of the outer packet. You know, this is if you run over the MTU between the tunnel concentrator and the end customer. And you know, likewise, you have to reassemble when you get it back. So Pierre's came up with a very clever scheme to do virtual reassembly of V6 packets, which is in the code, right? Yeah. Reals. No, we don't do real. Do we do real assembly of V6 packets as well?
We do not reassemble at all.
Right. Yeah. So we do. You know, if you.
That I mean, we still do just like if we did.
Right.
It's a trick.
Yeah. So if we get a V4 fragment inside the tunnel, we'll just decap and forward. If we get a fragmented V6 packet, we'll pretend that it was a V4 fragment and do some magic bit handling to make it look like a fragment. So we spew out V4 fragments on the other side. That might have some unintended consequences on the you know, when you send that out on the internet. Fragments don't fare well. But if you know, if you want to do tunneling, that's, you know, have a look at that code. It's in the map directory or in the ipfrag directory, because at least you'll get some good ideas, I think, on how you can deal with these MTU issues. But again, you know, just make sure the MTU is large enough, and you don't have to do that. That's kind of the basic rule. And if you can't do that, you are in you know, problematic space. Right. So this is NCAP. So we also support translation. So it saves, you know, 20 bytes overhead. It's and that has another interesting use case, which we see more and more. I mean, this mechanism allows an ISP to turn off V4 in their network and then just tunnel V4, look at V4 just as a service that they provide to the edges. This mechanism here with translation does the same thing for your data center. So now people are looking at building IPv6 only data centers and providing V4 just as a service on the edges. And you know, this stateless translation is a pretty neat way of doing that. You typically would have, you know, a lookup table for each you know, server inside its V6 address, and then its external representation as a V4 address. At least quite a few people have come to the realization that, you know, running a dual stack network is a pain in the arse. I mean, it's not necessarily twice as much work, because you have to run IPv4 and IPv6 side by side. But it is more work, and it's more things that go wrong, and it's a lot easier to run a single stack network, and that's why people just, you know, want to do V6 on the inside, where there's no issues of running out of addresses, and then just map these to you know, some public representation as V4 for public services. And many of these data centers just, you know, you run out of space in 10/8, for example. So you have to have overlapping private address space if you were to use V4 on the inside and things like that. So that's so we're seeing quite a pickup of V6 only networks. And thinking on how poorly OpenStack and Docker and all these open source projects do for V6, that's, you know, at some point we hope they will wake up, because you will see these networks being V6 only, and think if you built a data center today, you should probably look very hard at doing it v6 only. As I said, I think we're doing, on a reasonable core, we're doing about 6 million packets per second per core, and we'll scale almost linearly with the number of cores. So what we tested with is a platform with 12 10 gig interfaces. I don't know if, Magic, did you test map with 40 gig as well interfaces? No. But you could put, at least 120 gigs worth of v4 traffic in a single bare metal server. So at least my expectation is that most of the v4 internet will run over this, will run VPP. There are some big service providers looking at these kinds of ideas, ways of doing it. I tried, initially, being from Cisco, we tried to see, and we have support for this in platforms, hardware platforms. But the pleasure of doing this in VPP is just, it's just software, right? You can just experiment with different mechanisms for fragmentation and reassembly, for example, much harder to do in a hardware platform, right? And we can evolve much quicker as these mechanisms evolve, and we can pick some winners. And compared to if you were to run this on an ASR 9K, for example, which you perfectly well can, it has very different scaling properties, right? Here I just need more capacity. Well, let me just spin up another VM or spin up another container or add another commodity server that is probably already racked into some data center somewhere. Doing this on commodity hardware, I think is kind of the obvious thing to do. So we have quite a lot of mind share on using a VNF for this kind of thing. And of course, there's some consequences. So some people argue, Jeff Houston among them, that there's only for TCP in the v4 internet only port 443 works. So everything else doesn't work. For UDP, it's port 53, and those are really the two transport ports you can use, and these mechanisms sort of emphasize that you can't run arbitrary stuff over v4 anymore. You can't imagine, if it's not UDP or TCP, it certainly will not work. UDP barely works through the internet today, right? You have to build your transport protocol on top of UDP or on top of TCP if you want to do some innovation. But we are where we are, right? So v4 will degrade. It's already degraded, right? It's limited what you can do with v4. So for God's sake, get off of that that old thing. So here's the test setup we have with a 2-socket bare metal server with 12 10 gig ports, and we had an Ixia tester on the other side here to send traffic. Here's a demo setup we had up, but it was incredibly easy to write as a first project in VPP. I think still we're about the 1,000 lines of code. I think certainly the inner loop is very small. Going to prove that VPP as technology to do tunneling.
In terms of lines of code, the funny part is really that the things that the code spends 99.9% time doing is maybe a few hundred lines, and then there is all the exceptions.
Yeah.
Particularly for MapT.
Yeah.
Translation.
Yeah. And I think the cool thing also with kind of this modularity where you do the exceptions in separate graph nodes, you could actually leave it up to the operator. Do I want to have the exceptions included in the running code or not? I mean, you could just take those nodes out of the graph, and those you would drop packets instead of trying to deal with fragments, for example, and that would be customizable without very easily, without having to mess about with the core part of the code. Getting this thing up and going was just a few days of work, and then The rest of the time was spent on all the exceptions, of course. And you know, forwarding performance. This is really a base network routing function, trying to get as much highest number of packets possible through that box was our main goal. And perf top is certainly one good tool to see where your bottlenecks are. Please do, at least in VPP, we're trying to, if you do a feature, please make sure it works for both V4 and V6, at least V6. If yeah, it would be nice to see if we could do a build with without V4 just to tickle people's humor. The consequence of all these tunneling things are, especially for these ones that are, this is going to be the internet connection for people. You have to support 1500 byte payload for V4, which means that you have to carry 1540 byte packets around the network. And that's certainly easiest to do in a single buffer, right? Don't chain buffer for those last 40 bytes. So, I think the default buffer size is about 2K, right? So 1540 fits, I think. Yeah. 2K, yeah. Plus, overhead in front. So yeah, it's very cool for fast prototyping, getting a service to see how it works in performance in a very short time. Learning curve is steep. Yeah, now you've gone through that part, right? Now you're already in the in the way where you can start coding. So this is probably certainly the first kind of running in real networks bit of VPP. I think we'll see. Yes, question.
Is there anything specific to be done to prevent some DDoS attacks? Is there any way that the code could be, let's say, could support some DDoS attack based on some randomness of traffics, based on specific ports, specific fragmentation IDs?
We are doing quite well on that. So we, statelessly just forward packets. We have some state in that fragment cache, which is a circle buffer, which is configurable in size, but very small. So the only consequence is that you will overflow your or overwrite your cache for new packets, such that legitimate fragmented packets will not get to where they want to go. But yes, if we didn't have bounded data structures, we would be an easy victim of DOS attacks. But right now, you can tune the size of those buffers and the timers or timestamps actually for how we try. So there's some code in there to try to identify, what would look like a DOS attack versus a legitimate fragment, right? At least you try to leave things which you forwarded against.
DDoS fragments and legitimate fragments. Right. So we just do our best, but the idea is that once you do the job at line rate, and everything is stateless or almost stateless, only the fragments or reassembly may not be stateless. It's hard to DDoS that.
Since, as you said, most of the traffic is TCP. One of the issues with TCP, you have the don't fragment bit.
So we have well, it's not only in TCP, right? V4 has.
Yeah, but most deployments we see this bit with the TCP. So, what should be the option in that case? Just ignore the don't fragment bit.
So this would be the case where you had the fragment, right? And that would typically be between the tunnel concentrator and the customer, running across the ISP's own network. So the first recommendation is make sure that your MTU is managed such that you don't have to fragment, because if you have to fragment, you're creating trouble, right? But if you have to, we have an option of overriding the DFB and ignoring it, so we can do inner fragmentation anyway, because we do prefer to do inner fragmentation. But this is depending on service providers. Some service providers want to do outer fragmentation, so you fragment the V6 packet, then the CPE has to reassemble. If you do inner fragmentation, then the host has to reassemble. or well, essentially the NAT service on the CP anyway, so it doesn't matter so much. But yes, it's there is actually an RFC going through this and saying, you know, sure, yeah, you might just ignore the don't fragment flag if you know what you're doing. So we do have an option for that.
And what about the options of tweaking the MSS of the SYN packets just to be sure that it's always small enough in the core network when we cross a map gateway
from the internet to
yes.
the CPE, you mean?
Yeah.
I really don't want to get into the business of messing with customers' payload too much. I mean,
because that was a common practice in L2TP, for instance, years ago. People were, let's say, hijacking the MSS just to be sure.
Right.
That,
so in this case, the MSS is often rewritten by the customer CPE, you know, going out, right? Lots of you know, cloud providers set a very small MSS anyway. You know, both for V4 and V6, I think, to accommodate for tunneling. I think the default Google, for example, V6 is 12. What is it? 1220 bytes, I think. At least, you know, quite far below 1500 bytes. Well, we don't want this to work well, right? We want people to move off V4. You know, people should feel the pain. You know, this is shared pain. How do you make people move? You know, make them suffer. But yes, we really don't want to mess more with the payload than we have to. Any other questions on?
In deployments, do you actually see people fragmenting?
In the ISP network,
yeah.
So most people would just say, well, we have 9K anyway, not a problem. The last leg is typically the problem, that there are some, you know, DSL deployments where you have, you know, a smaller MTU, like, you know, 4092 or something, if you run, you know, PPP.
So it is a real problem.
For some, yeah, in some cases it is, yeah. But you know, if you're not 1500 today for V4, you know, already into, you know, rewriting MSS and hoping that. So we do support path MTU discovery, so we can send, you know, ISMP packet to big messages back. They don't fare too well in the internet either, right? So but at least we you know, we try to be as RFC compliant in this implementation as we possibly can. But you know, that's, you know, the other answer, right? That ISMP send a packet too big, and then the host on the other end would lower the TCP MSS. Of course, that depends on the don't fragment bit being set as well. So I think, you know, largely we punted that problem as well, and saying, you know, I don't think we can solve this problem at the network layer. So if you want to do path MTU discovery, you have to do it in the transport layer. Someone else's problem. I'm on the network layer. But there's not much progress there either. So yes, all these issues are problematic for, you know, for any overlay. We try to deal with them as much as we possibly can.